Welcome you all to the video lecture of Introduction to Electrical and Electronics Engineering. So here in this video lecture we are going to get discussed to the topic related to that of the ACA fundamentals. In the previous video lecture we have discussed regarding to that of measure nodal analysis, followed to the of our physical classroom discussions. So here this AC fundamentals is going to get deals us with the initial basic terminology such as to that of basic things is required for the AC circuits. So accordingly to that of course outcome, here this AC fundamentals is get related to that of the CO1. So applying the basic losses and simplification techniques in the electrical engineering using the electric circuits with respect to that of apply level conditions as the questions may be get covered. So here in this presentation we are going to discuss the magnetic circuits definitions of the magnetic quantity in detail. So these are the basic definition process get involved in this presentation. So magnetic flux, flux density, MMF, magnetizing force, permeability, relative permeability, reluctance, and the permeances. So these are the basic definitions of the magnetic circuits that going to be get discussed clearly in the following presentations. So the magnetic flux, here this magnetic flux normally says to the top the how many amount of the magnetic line quantitatively produced by the magnet. So let for an example, here this is the magnet. So according to this magnet, how many magnetic line it going to get produces. So that is to the top the magnetic flux. So here this unit is related to the top magnetic flux is 1 Weber. So the 1 Weber includes to the top the 10 to the power of 8 magnetic lines. So consistingly this magnetic line we are going to say that as a Maxwell. So the normally the magnetic flux going to get denoted in the top side. Here its unit is a Weber. So normally the 1 Weber says to the top the 10 to the power of 8 magnetic lines, which means that 10 to the power of 8 Maxwells. So now we are going to discuss to the top the characteristics. So normally this characteristics says to the top the magnetic flux lines is produced in the magnet. So first of all we can go through the point number of 5 and 7. Let for an example, let assume a magnet, so a north pole. So another magnet is also a north pole. Normally in practical we can able to observe that this both same side pole doesn't get attract, it automatically get repels. So let for an example, this is the north pole magnet and this is the south pole magnet. Normally what it get attracted to each other, so that it get discussed in this 5th and 6th point. So the lines of the magnetic flux closer to each other and having the same direction repel to each other, whereas the opposite sides of the poles is automatically get attracted to that each other. So the next thing is we need to get remind in our mind regarding to that of magnetic flux is it doesn't go for any physical existences. It is beyond to the top imagination terms. So this does not involve to the top the physical existences. So the second and third points is third points and fourth points is to the top there. These magnetic flux lines were never get intersects. So and those magnetic fluxes are always in the closed loop by itself. It get produced means it automatically get closes. So closed loop by itself only. So the another characteristics is the direction of the magnetic flux lines is automatically get defined by its the direction in which an north pole would move it where it placed in that of magnetic field. So these are the characteristics of the magnetic flux line. So the next thing is the magnetic flux density. So here this magnetic flux density is normally notated in the term letter B. Here this magnetic flux density is going to say that the flux per unit area are in the term to the top the right angle to the top flux. So with respect to the top term right angle to the top flux, this magnetic flux density going to be get defined. Here this magnetic flux density is defined by the top psi divided by A. So this unit tends to the top WB divided by the meter square. Here this WB is automatically get related to the top psi. Psi is not already we have seen to the top psi means what? The magnetic flux. Here this A terms is to the top the area of the cross section. So the unit of the magnetic flux density is the Weber per meter square. Here this Weber WB says to the top a magnetic flux, and the A in terms is to the top the area of the cross section. So the next property, which means that the next definition is the mmf. So in analogous of electric circuits, we deals to that of emf. Here we are get studied to that of the magnetomotive forces. Here this magnetomotive forces is generally got produced by the term of the fluxes in the magnetic circuit. Let for an example, a magnetic circuit is having means that circuit only going to get produce this flux. So this which means that the magnetomotive force. So let it is obtained by the product of the current and the flowing through a coil up to the top number of turns. Let for an example, here this coil is get connected to the top circuit. Here this number of turns is and the current flowing through the coil going to be says to the top the mmf. So let for an example, here this number of turns in that coil is the 4. So 1 2 3 and 4 number of turns is and into the product of the which means that the current obtained in that coil. So formula is F is equal to magnetomotive force N is equal to F is equal to N into I, the number of turns is into the current. So it's in terms of the ampere. So the next is the magnetizing force or the magnetic field intensity. So this magnetic field intensity or the magnetizing force it get defined with respect to that of the magnetomotive forces in terms to that of the per unit length of the magnetic flux path. So here the magnetizing force H is going to be get related to that of number of turns, current in that flux and the length of the coil. So with these parameters N, I and L, the magnetizing force to be get revealed how much of the magnetizing forces that the coil going to have in that circuit. So the next is the permeability. So normally this permeability going to be said to the top the proportionality principle, which means that here this B is directly proportional to H. H is a magnetizing force, and whereas this B is going to be the say to the top the flux density. Here the magnetic flux is already get indicated in what psi, whereas this B going to say to the top the flux density. So B is directly proportional to H magnetizing force. So in order to make this directly proportional to get constant, they are going to get use this mu. So mu is the constant proportionality. So that constant proportionality mu is going to be said to the top the permeability. So B is equal to mu into H. This is called as a permeability. The another thing is the relative permeability. So this relative permeability is going to be get defined to the top ratio of the flux density obtained in that medium and in terms to the top of vacuum. This relative permeability going to be get defined. So let the considering of that medium is the one factor, and surrounding vacuum is also the air space is also one of the constraint to get find out this mu r value. So the flux density obtained in that medium and to that of flux density in the vacuum. So the permeability for the consideration for the another material, any other materials is going to be get defined with the terms of mu is equal to mu naught into mu r, the relative permeability into the mu naught. Whereas this relative permeability considering for a vacuum or free space is a unity, and that of the air and the another other non-magnetic materials were nearly to equal to that of the unity. So the another definitions is such as the S and P is going to be said to that of the reluctances and the permeances. The reluctance is a property of the magnetic material where the we can able to get setup of the flux is opposed, which means that it is going to define to the top the ratio of the magnetomotive force in terms as to the top of flux, whereas this the unit of the reluctance is going to be defined to the top the ampere per Weber, where it is going to be get denoted to the top S. Whereas considering to the top permeance, it is directly reciprocal to the top the reluctance S. So in previous DC circuit we see it in a problem regarding to the top S in terms of to the top resistance. So normally the Siemens S is going to be get in terms of to the top the reciprocal to the top resistance. Like that here this permeance is the reciprocal to the top the reluctance. P is equal to 1 divided by S. So here this unit says to the top the Weber per ampere. So where it is in terms of to the top ampere per Weber. So the next thing we are going to get see over the top the magnetic circuit. Let for an example, let here we are going to get think over to the top a single magnetic circuit and a composite magnetic circuit. Here the single magnetic circuit is going to be get taken over according to the top of one single magnetic material, whereas the composite magnetic material involves to the top of complex terms, which means that adding to the top one or more magnetic material and how they are going to get taken place differently to the top specimens, offering to the top different magnetic properties. So here there only we are going to get considered over the non-magnetic things of the air space vacuum terms and to the top the magnetic part also. So those combination of the magnetic material and air is of a more practical importance. So the single magnetic circuit is considering obtained by using a single magnet having two poles as north and south, like that. So whereas the composite material having more number of magnetic substances that going to be get involved of the two different specimens, we can say that with to the of the two different magnetic properties. Let those things is those magnetic properties maybe it is a term to the of magnetic one or a non-magnetic one. So non-magnetic one we can get related to the of air or any vacuum terms. So normally this combination of the magnetic material and air is more what the practically important things is. So according to the of composite magnetic materials, the terms leakage coefficients is going to be get places a major role. Here this leakage term lambda is obtained with the terms to the flux density. So normally the magnetic fluxes is what is get denoted to the psi. So according to that, here the leakage coefficient lambda is also going to be get obtained by this flux density and lambda dash. So with terms to the top lambda and lambda is equal to psi plus psi dash divided by psi. So this leakage factor is greater than to the top the unity term. So this leakage in order to get cover over this leakage flux, the leakage coefficients get introduced. So that leakage coefficient is denoted in terms to the top lambda. So here in this video lecture we saw regarding to the flux, magnetic flux density and MMF, magnetizing force, permeability, relative permeability, reluctances and permeances detailedly. Thank you.